Hello, I'm Richard Hollingham. Welcome to another edition of the Planet Earth podcast. This week, coming to you from the beautiful, windy and unspoilt North Norfolk coast. Well, I say unspoilt, but I'm here to talk about the curse of plastics. It turns out you can't only find them here, you can even find them around the coastline of Antarctica. Also this week, we meet scientists in Sussex who are firing green laser beams into the night sky.
And as you can see,
oh wow!
The laser beam,
great.
Coming out.
No wonder the locals love it.
Yes, they do. Yes, yes. Quite spectacular. Yes.
And more on that in just a few moments. Well, with me on the shore here at Cley is David Barnes from the British Antarctic Survey. David, we've just been walking along the shore here, and the shingle beach is really between the grey sea under a grey sky, and then the salt marsh behind us, and then finally the village of Cley itself. What are we looking for on the beach?
So we're going to walk along two strand lines, one the storm line, where the last time that there was a big storm has deposited lots of natural debris, but also man-made things, and along the strand line from the last big tide. And we're going to walk along and look at some of the more persistent items of debris, particularly plastic, and see what it tells us about the ocean far away from these shores.
Well, we're going to head off along the beach, and while we do that, I want you to ponder this. How do you measure the exact position of a satellite orbiting the moon to within 10 centimetres? Well, that's what scientists from the Space Geodesy facility were able to do when they contributed to NASA's Robotic Lunar Exploration Programme last year. The only place of its kind in the UK, the facility can determine the exact position of up to 30 satellites at any one time. Sue Nelson went to see what it takes to track a satellite travelling at up to 18,000 miles per hour. And more importantly, to ask why you'd want to know.
In the grounds of Hurstmonceux Castle in East Sussex, there's an unexpected sight. There are two domes. One is a telescope and the other is a radar. They belong to the Space Geodesy facility, and it's well known locally for firing a single green laser beam into the night sky. Well, it's not quite night time yet, although the sun is setting, so I'll go inside to meet Vicky Smith. She's one of the scientists who works here, and she's in charge of the laser. Vicky, tell me about this room itself. There are quite a few computer screens and some almost museum-style equipment, although is that insulting the technology they're here? It does look very straight out of the 1960s.
Probably because some of it is. But we're in the control room at the heart of the Space Geodesy facility, and this is where we coordinate which satellites we're going to track, when we're going to track them, and tell each equipment how to interact with each other.
Now, you can't do this without a laser. Let's go inside the room where the lasers are so you can tell me a little bit more about it. Oh, it's definitely a lot cooler in here. It's like going into a large fridge freezer.
Yes, because we've got very, very sensitive equipment in here, all of the equipment has to be kept at a very stable temperature. If you get temperature effects with the equipment, you get instabilities in our measurements.
This box in front of us, I assume, contains the equipment that's producing that beam that you can see at night.
That's one of them, yes. We've got two lasers on site. It fires at 13 times a second with a 100 picosecond pulse length, and a picosecond is a millionth of a second.
And how powerful is this beam?
We're talking hundreds of megawatts of power.
Which begs the question then, if you're firing a laser beam into the sky towards a satellite, how safe is it?
It's not going to shoot down aircraft.
Glad to hear it.
Yeah. And also, because the light is diverging, so it's getting larger as it's going out, it's not hugely damaging, but it is damaging to the human eye, which is why we've got a radar system which automatically will shut down the laser if it detects an aircraft coming over. So I've just switched on the electricity for the main laser, and I'm just powering up each of the amplifiers. Just wait for them to energise. We've got to simmer the flash lamps to get it going, and then we can get her to fire. So what we've got in the background here is large capacitors discharging all of their electricity into flash lamps, which are actually in the amplifier modules, which is generating the laser light, which is then travelling up one side of the laser, back down the other, and then bouncing out to the telescope. So the laser light actually travels through 5 mirrors up to the telescope sitting on top.
I'm now outside the facility. The sky has darkened, the first stars have started to come out, and I'm with Christopher Potter and Graham Appleby, and we're about to go up these stairs now into the observatory itself. Torch on, into the dome now, round at the base and up another flight to metallic stairs right into the canopy of this dome. Christopher, how big is this dome?
This dome is a 5-metre dome.
And oh, what's that sound?
That's the proximity detector. That's saying that somebody is outside, or it could be a rabbit or a badger or whatever.
Well, we'll assume it's friend rather than foe. Is this telescope here, which is several metres high, directly above the laser beam that I saw?
Yes, it is. The laser beam comes straight up to the centre of the telescope and then actually sort of does 3 90-degree bends, and then a laser beam is emitted from a small telescope at the side of the main telescope, which collects the photons of light after they've travelled through the atmosphere and back again.
Well, in order to get an idea of what happens next and how it works, I suppose we have to see it in action. So, Graham, what do we have to do for that?
As you see at the moment, the dome is closed against the elements outside. So to prepare for observing, we have to open the telescope dome. And you hear it opening now. It's an eyelid dome, so it opens down to a very low elevation, so the telescope will be able to see satellites all over the sky without rotating the dome, which is usually the case in a traditional observatory, but in this case it doesn't. So as you can see now, we can see the whole sky.
It's beautiful,
whole
isn't it? It's
horizon,
lovely,
yes.
even though we were just outside. There's something about having the ceiling above you part and
Yes.
open. And
You're
then...
part of it here now, yes.
But it's not the stars you're interested, it's the
It's not.
satellites. How do you know where the satellites are?
Through a series of observations made by ourselves and by the international community of which we belong, we are able to predict the satellite orbits to an accuracy of a few metres in some cases. So we already know where these satellites are at that level, and then we can track them and fire the laser at it and make millimetre-level precision observations.
And are there any satellites that are orbiting the Earth at the moment that this telescope can track?
Yes, there are. There's some navigation satellites which have their own method of determining where they are, but we can use our laser ranging observations to check on that and improve on the precision. So I can now move the telescope to track one of those by entering its coordinates on this computer, and you can hear a few things happening on the telescope. It's adjusting the divergence of the laser beam.
Now the telescope is now
And the telescope
spinning
is
round
spinning
on its
round.
axis.
Yep. And it's going to go pretty accurately to point at this satellite, which is orbiting the Earth 20,000 kilometres above the Earth.
Not quite 360 degrees, it's sort of
It's about
270.
270,
So
yes,
yeah,
that's right.
3/4
Yeah.
of the way anti-clockwise now to point to a different direction of the sky.
This satellite itself takes 12 hours to orbit the Earth, so it's very, very slow moving. So even though the telescope looks like it's stationary, it is actually tracking the satellite very, very slowly. And in fact, on this computer screen here, this bright dot there is the satellite. That's the sunlit satellite, image of the satellite. And the fact that that image is staying stationary on this computer screen shows that we're tracking it very well.
The laser itself, Christopher, we've got the laser to the point where it can come out of the telescope. You take the positions that we've just been shown here, and then is it a case of just firing the laser towards the satellite in
It
order
is.
to hit it?
Yes, by use of the fire switch, the filter downstairs is taken out, and as you can see,
Oh,
the
wow.
laser beam
Great.
coming out.
And there's a great long green laser there, just the sort that you'd see in some sort of pop show,
Yes.
stretching out way into the sky. No wonder the locals love it.
Yes, they do. Yes, yes. Quite spectacular. Yes.
Graham, then, this laser now, when it gets to the satellite, what are you aiming for? Are you aiming for it to just reflect off the satellite, similar to radar?
Yes, that's right. This particular satellite carries a cluster of, I think, 100 corner cube reflectors, whose sole purpose is to direct the light from its source back to the source. so turn the light pulses through 180 degrees. So the telescope that we've had just described is waiting to receive those few photons that make the return journey. And don't forget, this is 20,000 kilometres up, 20,000 kilometres back. And although we're sending a huge number of photons up, it really is only one or two that make that return journey.
And why is it so important to know the accuracy in terms of position of a satellite? Because let's face it, the space agencies know where the satellite is. So why do we have to know to a millimetre precision?
It's the science driver for this whole work, is to determine position on the surface of the Earth to millimetres, and then to use those positions, those very precise positions of such telescopes as ourselves, to track the Earth observation satellites such as Cryosat, Envisat, ERS-2, that are making radar measurements to the oceans, the ice sheets. Now, you really wanted to say whether the ocean sea level is changing, and it's going to be at a few millimetre level. So you need to remove any source of error in the satellite position by making these kind of observations. As you say, the space agencies know where the satellites are for their radio transmission communications, but that's at metre level, which is no good for the science that we're trying to do with this sort of work. Millimetres matter.
Graham Appleby, head of the Space Geodesy facility, ending Sue Nelson's report. And you can see pictures of the facility on our Facebook page. Don't forget that for the latest news on the natural world, do visit the Planet Earth online website. This is the Planet Earth podcast, the only science podcast I know of that's always recorded on location. And the location this week is on the beach at Cley in North Norfolk with David Barnes from the British Antarctic Survey. And we've been looking for plastics during the last few minutes. What have we found so far?
Some of the usual suspects, such as bits of plastic twine, some pens, spoons, lots of bottle tops, bits of polystyrene foam. Quite a wide collection of things, not some of the things I was expecting to find. I thought we might find some flip-flops and trainers and cigarette lighters, the normal things, but we haven't found any of those.
So we've got here is a plastic bag, and I think we can probably tell from the green lettering which supermarket that's from. This is, it's torn and it's gone sort of translucent, but it's still retained its essential plastic bagness.
Yeah, plastic bags are made of very, very thin plastic, so they break down relatively easy with salt spray and UV light as long as they stay in the top layer. But even this could have travelled quite some distance, and we can see that looking at it closely, you can see all sorts of things have started to get a grip on top of it, including foraminiferans. So life has started to colonise this plastic bag.
That's amazing. You've also got down here, we think this is probably the heel of a shoe. It's a sort of bit of sort of woody, fibrous piece. I'm kind of breaking that up. That's kind of breaking up quite easy, but it's moist. It's, again, you can imagine that attracting life.
What will happen with a lot of this material is when it starts to get broken up, the surface has got a very good texture for settlement because it slows down the water over it. Its boundary effect will be slightly stronger than the smooth pebbles and other smooth things that are typically floating. So life can get a grip and then it can be carried around. But it's not just life. These plastics will absorb all sorts of things such as toxic chemicals and transport those around as well. And so various groups over the UK and elsewhere have been studying what plastics can carry, how far they're carrying them, and what sort of effect they have.
And that, for you, is almost a bigger issue than, yes, they're not aesthetically pleasing to see on a beach. Here we've got a green bottle top, there's a little bit of string here, the plastic bag. But it's the fact that not only do these spread toxic chemicals in the environment, they carry life around the environment.
Yeah, and we can see on this piece of plastic twine that we've actually got two different species of hydroids. You can see one on the base there and another one halfway up, and they're actually reproductively active. They'll be releasing larvae, so this is not just transporting the adults around, these will be producing larvae that will settle wherever this goes.
So these tiny little, almost twig-like projections on the side, they're alive, and so they kind of mingle in, they almost become part of the twine there.
Yeah, and actually I found a third species. So we've got three species just on this insignificant little piece of twine. Now, these species are probably native to the UK, but there'll be other species that come in that aren't. And that's where the problem is, that it can make a big difference to local aquaculture and fisheries if some alien pest gets in, becomes established, and then really starts to outcompete or eat our native fauna. And with these pieces of plastic travelling for many years, perhaps decades, that means we could get animals and algae and other organisms from all over the world landing on our shores.
Now, you're concerned primarily with the Antarctic, being from the British Antarctic Survey. When you found plastics around the Antarctic, were you shocked by that?
Yeah, I suppose a normal person would be shocked, but I'm a cynical scientist, so I wasn't greatly surprised. Perhaps I was surprised that some of this material could have travelled very far, perhaps even outside of Antarctica, which means it's across the polar front, which is really quite a strong barrier. But it's been well established that lots of material is washing up on the shores of the northernmost reaches of the Antarctic, places like South Georgia, where it can be a big problem by being swallowed by things like albatrosses and other seabirds, and banding tapes that get stuck round seals and stop them growing and can suffocate them or sort of strangle them.
This is the big question, is what can be done? I mean, it doesn't, I suppose, matter that there's this twine with this life clinging onto it here, but it might matter in other parts of the world.
Yeah, I think it still matters here. We still have a problem with invasive species having a big effect on coastal industry, and especially industry that involves sea farming. And so, yes, it is still a problem here, but it is more a problem elsewhere. We have to remember that looking along this strand line here, we can see lots of natural material. We can see seaweeds and we can see bryozoans and other animals, especially crab shells, that have floated here naturally. And they've been doing this for a long period of time. For hundreds of millions of years, life has been floating around this part of the world. But in the polar regions, where there aren't lots of things that float, there aren't shells that naturally float, and there aren't seeds and logs and other material that we would naturally see on our strand line, then plastics there and other floating man-made debris has made a huge difference, because it's created this new environment of things floating on the surface, transporting organisms that wasn't there before.
And all this stuff, I suppose. I mean, let's go through. What have we got in our little collection here? We've got a bit of a plastic bag. We've got a bottle top there. We've got what we think's the heel of a shoe. We've got the twine here. We've got, what's this? This is a cable tie. We've got this odd bit of foam. It looks like almost from cavity wall insulation or something like that. And you can imagine that's perfect for carrying life around. And I suppose all this, I mean, none of these things would have even existed 50 years ago. So this is a very new problem.
Yeah, it has massively expanded the options and possibilities for life on an ocean wave. So for organisms, and there are a bunch of organisms that naturally live in this environment right on the sea surface called Neuston. And for those animals, this is a real bounty. It's really increased their possibilities and things to lay eggs on and to keep as shelter. So for those, it's a real boon. But for other organisms, it's transporting them to places they never would have got to, which is a real problem for us, and also our native shoreline. So if we look along the shores around the UK, it's very hard to find a place anywhere without alien species. And one of the ways they're getting there is on this plastic that's floating at sea.
Well, David, thank you very much. I think it's starting to rain, so a good time to retreat. We'll put some video and pictures of the beach here on our Facebook page. And all the podcasts we've ever made are available to download from the Planet Earth online website, including our recent podcast from the Arctic sea ice. You'll also find news, features and blogs on Planet Earth Online. And that is the Planet Earth podcast. I'm Richard Hollingham from the beach here at Cley in North Norfolk. Thanks for listening.